Our planet is floating in a universe that's unimaginably violent. I'm going to count down 25 cosmic disasters that could erase all life on Earth. You'll get a new understanding of how fragile our place is here and the ultimate fate that's waiting for everything. We'll look at how a silent threat from deep space could sterilize our world in an instant. And we'll see why the laws of physics might one day rewrite our reality, what it means to live on a speck of dust in a cosmic shooting gallery. Earth feels solid. It feels permanent, but it's a temporary shelter. The universe isn't some serene, distant place. It's chaotic, it's violent. Giant stars die in supernova. That happens all the time. It rips solar systems apart. Then there are gamma-ray bursts, beams of pure energy, so intense they can outshine a whole galaxy for a moment. They cut through space like a blowtorch, and galaxies themselves, these huge islands of stars, they collide, they merge. It's a slow-motion cataclysm that rearranges everything. These aren't rare events. This is the background noise, the normal state of things. For billions of years, Earth has just been lucky. We've been a lucky traveler. Our planet has a molten core. That core generates a magnetic field. It's a shield. It deflects the sun's most dangerous radiation. Our atmosphere is a blanket. It burns up smaller threats. It regulates the temperature, and we orbit in a quiet neighborhood, a calm part of a calm galaxy. But that luck isn't a promise. History shows our safety is conditional. The dinosaurs are proof. Their resting place is marked by a crater in Mexico. That crater is a monument. It marks a time when something from space reshaped everything. A single rock changed the course of life, and that was just a pebble thrown by our own solar system. The universe has much heavier artillery. To understand our future, we have to look at it. We have to look directly at these mechanisms of annihilation. Our own solar system is the first circle. It's the one we think we know, but it's full of sudden, violent threats. Then the circle gets bigger. That's our local neighborhood in the galaxy, where dying stars can send out these silent blasts. They sterilize everything. And then the largest circle, that's the whole universe, where the laws of physics themselves could change, rewrite reality. In an instant, this framework matters. It tells us how the world might end, but it also tells us when. Some of these events are like a gunshot, one catastrophic moment. Others are more like a tide, a slow rise, so gradual you might not even see the point of no return. And the unsettling part is that for some of these, it's not a question of if. It's when, on a long enough timeline, they become certain, statistical certainties. So we'll start with the threats closest to home, the dangers right here in our backyard. And then we'll expand the view to the galaxy and beyond, to the truly staggering forces. The sun is our greatest protector. It's been there for billions of years, this steady heartbeat. We take it for granted, but stars aren't static, they're churning. Our sun has a temper. We see it in solar flares, those explosions on the surface. We see it in coronal mass ejections, these huge clouds of plasma launched into space. Normally, our magnetic field catches all that. It funnels the energy toward the poles, and we get the auroras. But astronomers have seen other stars do something else. They've seen superflares, eruptions that aren't just 10 or 100 times stronger than what we've recorded. They're potentially 1,000 times stronger. And the evidence says it's possible here. If our sun did that, and if it was aimed at us, everything changes. The first sign is a flash of radiation. Then, a day later, the coronal mass ejection arrives. This isn't a nudge to our magnetic shield. It's a sledgehammer. The shield buckles. The geomagnetic storm that follows would be beyond anything we know. The whole planet gets wrapped in this net of surging electrical currents, and those currents find the path of least resistance. they find our power grid. The transformers, the massive ones that regulate everything, they overload. They melt or explode. The grid collapses, not in one city, across continents. Satellites get fried. Communication, GPS, financial systems, all of it goes dark. The event itself doesn't hurt anyone directly, but the aftermath is a different kind of catastrophe. We're thrust back more than a century in an afternoon. Without power, the pumps for water and fuel stop. Refrigeration fails. The supply chains that feed cities, they rupture. This isn't a temporary blackout. Replacing those giant transformers takes years. We don't have many spares. The recovery would be measured in decades. It's a reminder, our technological civilization, for all its sophistication, is built on a foundation that's vulnerable. The sun gives life, but with one violent convulsion, it could take away the world we've built. A solar superflare is a sudden shock, a single catastrophic blow. But what if the end came not with a bang, but with a slow, relentless simmer? A change so gradual you might not even see the point of no return. That brings us to a second disaster, one that turns our own atmosphere against us, a runaway greenhouse effect. You've heard of climate change, the gradual warming. But a runaway greenhouse is different. It's a chain reaction with no brakes. Think of the atmosphere as a blanket. A thin blanket keeps you warm, but if you keep adding layers, the heat gets trapped. It can't escape. On Earth, the main greenhouse gas is carbon dioxide, but water vapor is far more potent. Here's how it starts: a sustained warming, maybe from the sun slowly growing brighter over billions of years. Or from a long period of massive volcanic activity. It causes the oceans to get warmer. Warmer oceans evaporate more water. That puts more water vapor into the air. And water vapor is a greenhouse gas, so it traps more heat. More heat means even warmer oceans, which evaporate even more water. The cycle feeds itself. It accelerates. The planet's temperature begins to climb not in degrees, but in tens of degrees, then hundreds. At a certain threshold, a tipping point is crossed. The oceans don't just get warm, they begin to boil, not in a pot but across the entire planet. Vast clouds of steam envelop the world, creating an even thicker, hotter blanket. The surface temperature soars to levels that can melt lead. All liquid water is gone forever. The atmosphere becomes a crushing, toxic soup of carbon dioxide and steam. This isn't a theory about what could happen. This is a description of what did happen to our sister planet, Venus. Venus is almost the same size as Earth. It may have once had oceans, but sometime in its past it suffered a runaway greenhouse. Today, its surface is a scorching wasteland under a crushing atmosphere. A permanent monument to what happens when a planet's climate system tips past the point of no return. For Earth, this ultimate fate is likely billions of years away, driven by the sun's natural aging. But the mechanism itself is a lesson in planetary balance. It shows a climate isn't a static thing. It's a dynamic and sometimes fragile system. Once certain feedback loops are engaged, they can lead to a new state. A state from which there is no coming back. The universe has something even more precise and devastating than a solar storm. Think of a star, a giant one. Much more massive than our sun. When it dies, it doesn't just fade away. It collapses in on itself, a final catastrophic act, and sometimes from its poles it shoots out twin beams. Beams of pure, concentrated energy. That's a gamma-ray burst. It's the single brightest thing in the cosmos since the Big Bang. For a few seconds, it can outshine an entire galaxy. 100 billion stars, all that power is focused into a narrow jet, like a cosmic blowtorch. And if that jet is aimed at Earth, even from thousands of light years away, it's a death sentence. There's no warning flash to see. The first sign would be the radiation itself, hitting our upper atmosphere. For maybe 10 seconds or a minute, our planet is bathed. Flooded with high-energy gamma rays and X-rays, the effect is chemical. It shreds the molecules in our ozone layer. In that brief moment, the shield that took eons to build is torn apart. Then the burst ends. The sky looks normal, but the damage is done. The real disaster comes later, in the days and months that follow. With the ozone layer gone, the sun's ultraviolet radiation pours down. It's a silent poison. On land, it would scorch plant life, collapse the food chains at their base. In the oceans, it would penetrate the surface, devastate the plankton. The foundation of the marine ecosystem, the radiation would cause widespread genetic damage, a wave of mutations and illness, but that's not all. The gamma rays would also trigger chemical reactions in the atmosphere, creating vast clouds of nitric oxide. These clouds would eat away at more ozone, and they would block sunlight, plunging the planet into a sudden, severe global winter. A double catastrophe, first a burn, then a freeze. The fossil record suggests this might have happened. Some researchers point to a mass extinction over 400 million years ago. The Ordovician-Silurian extinction. The patterns of species loss align with what a gamma-ray burst would cause. It's a humbling thought. A star dying in a faraway galaxy could reach across the light years, erase most life on our world without ever touching it. Our fate, in that case, is written by the violent death of something we might never have seen. It's the ultimate example of our cosmic vulnerability. We're not just living on a planet, we're living in the line of fire. The dinosaurs had no warning. A rock maybe 10 kilometers wide, moving 20 times faster than a bullet. It hit, and it wasn't just an explosion. It was a detonation on a planetary scale. The energy released was like millions of our biggest nuclear weapons all at once. The immediate effects are hard to grasp. The impact vaporizes rock, creates a fireball that burns everything for hundreds of miles. Then the shockwave comes. It flattens forests and starts earthquakes that shake continents. And then the debris, millions of tons of pulverized rock and soot thrown high into the atmosphere. It doesn't fall back gently. It rains down as glowing, superheated fragments, and that ignites firestorms across the globe. The whole planet becomes an oven. But that's just the start. The real killer comes later, in the months and years after. That thick blanket of dust and aerosols, it doesn't clear. It lingers, circling the planet, blocking the sunlight. Temperatures drop, photosynthesis stops. That's an impact winter. It can last for years. Agriculture becomes impossible. Ecosystems collapse, starting from the bottom. The food chain breaks. This isn't a movie plot. It's the leading scientific explanation for how the dinosaur age ended. The story is written in a layer of clay, found all over the world, that's rich in iridium. That clay is the dust from that ancient impact, a global tombstone, and it tells us this is something that happens again in our solar system. We live in a cosmic shooting gallery. Millions of asteroids and comets orbit the sun, and sometimes their paths cross ours. There are programs like NASA, a Planetary Defense Coordination Office, that work to map and track these objects near Earth. But the historical record is clear. On geological timescales, a major impact isn't a question of if, it's when. It's one of the most immediate, tangible, existential risks from space. A reminder that our world's history can be rewritten in a single, blinding flash from the sky. Our planet has its own destructive power. It's sleeping beneath us. A supervolcano isn't a mountain, it's a caldera, a huge depression in the crust. It marks a reservoir of molten rock, hundreds of miles wide. When one of these erupts, it doesn't just spew lava. It empties itself. The force can be thousands of times greater than any eruption we've recorded. The immediate blast would be apocalyptic for that region. But the real global killer is what goes into the sky. An eruption that scale would send cubic miles of ash into the stratosphere, billions of tons of sulfur dioxide. Up there, the sulfur dioxide forms aerosols, tiny reflective particles. They don't rain out, they spread. They form a veil around the whole planet. That veil reflects sunlight back into space. The result is a volcanic winter. Global temperatures could drop 10 degrees or more, and they'd stay that way for years. Imagine a world where summer never comes. Crops fail season after season. Global agriculture collapses. Our stored food would last months, not years. The hardship that follows would reshape human society in ways we can barely imagine, but this is where the cosmic connection makes it worse. Could something from space wake this sleeping giant? A large asteroid impact. Its immense seismic energy could act as a trigger. The shock waves through the crust wouldn't just cause earthquakes, they could destabilize those massive magma chambers. Prompt an eruption, or worse, synchronize multiple supervolcanoes. That's the nightmare scenario, a 1-2 punch from the cosmos and our own world. An impact delivers its own winter, then the planet itself responds. It deepens that winter, extends it for centuries. It links two separate existential risks into one compounded catastrophe. It shows our greatest dangers might not come from just one source, but from a terrible synergy. The Earth isn't a passive stage for cosmic events, it's an active participant. It can amplify a disaster into an extinction. 5 billion years. It's a number that's just too big to really feel, but the clock's already running. Our sun, this thing that gives us everything, it has an end date built right in. It's a main sequence star. That's just a way of saying it's in the long, stable middle of its life, where it's fusing hydrogen into helium at the core. And that process, it can't go on forever. Eventually, that hydrogen fuel in the center, it's going to run out, and when it does, the star starts to die. It's not a quick explosion, it's a slow change, an inevitable one. The core, now full of helium, it'll contract, it'll get hotter. That new heat pushes the sun's outer layers outward. It swells, it keeps swelling. Over millions of years, our yellow sun becomes a red giant. This bloated red sphere, it takes up a huge piece of the sky. The inner solar system gets remade. Mercury and Venus, their orbits end up inside the sun's new, thin outer atmosphere. Those planets get swallowed, vaporized. Assimilated. Earth's fate is trickier. Our orbit might put us just outside the star's physical reach. We might not get engulfed, but that's not being saved. Because as the sun expands, its brightness, its energy output increases thousands of times over. Long before any contact, the planet faces this unbearable, rising heat. The oceans don't just warm up, they boil. That water vapor gets stripped away by the solar wind. The atmosphere gets scorched off. The rocks of the crust, they start to melt. The surface turns into a global sea of magma. Earth becomes like Venus, but worse, a barren, glowing ball of rock orbiting inside an oven. This is the ultimate guaranteed disaster. It's written into the basic physics of stars. Every world orbiting a star like ours faces this definitive end. Their biospheres, no matter how lush, they're temporary. They get a window of time, billions of years, but the window always closes. It's a perspective shift. We think of cosmic threats as outside things, asteroids. Gamma rays, a passing star, but the biggest threat is the heart of our own system. The source of our light and warmth is also the engine of our final end. It tells you that planets and the life they might hold, they're ephemeral, temporary features in a universe where even the stars are born and live and fade away. Our solar system's story has a final chapter already written, and it's fiery. Our sun is fixed for us, the anchor of our planetary system. But that stability is just an illusion, a product of our short timescale. The galaxy is moving, hundreds of billions of stars in a swirling dance, and stars pass by each other. They have close encounters. Think of our solar system not as an island, but as a ship. Sailing through a crowded sea, Most other ships are far away, just points of light, but sometimes one could sail right through our fleet. The gravity of a passing star is immense, even if it misses our sun by light years. It tugs on everything in our system. The most vulnerable things are at the very edges, the Oort cloud, a huge spherical shell of icy comets, a light year out. They are held by the sun's faintest whisper of gravity. A passing star's pull is like a sudden gust of wind. It disturbs that balance. It can shake loose thousands of these bodies, millions of them, sending them falling inward on long, elliptical orbits, crossing the paths of the inner planets. That's a comet shower, a bombardment lasting not days but millions of years. A relentless pelting of the inner solar system. Earth would see a dramatic increase in impacts. Each major comet strike could trigger its own impact winter. The planet would be in a state of perpetual climate chaos, ecosystems with no time to recover. But that's the gentler possibility. A more direct interaction could do something far worse to Earth itself. If the geometry is right, the star's pull could give our planet a gravitational kick. It could alter our orbit in a fundamental way. One path sends Earth spiraling outward, away from the sun's warmth. We get ejected from the solar system entirely, becoming a rogue planet. A dark, frozen world adrift, all oceans frozen solid. The other path is the opposite. That same kick sends us spiraling inward toward the sun. The orbit shrinks, temperatures rise, and we meet that scorching fate from the expanding sun, but on a much faster timeline. This isn't science fiction. Astronomers have seen stars with odd, hyperbolic orbits in our galaxy paths that suggest they were flung away by such an encounter. And simulations show that over the galaxy's multi-billion-year life, a close stellar passage isn't just possible, it's probable. Our solar system has likely experienced this before in its deep past. And it will almost certainly experience it again in the distant future. It points to a profound truth. Our planetary home isn't just vulnerable to rocks and radiation. Its very place in space, the orbit that gives us seasons and years, is contingent. It depends on the peaceful, uninterrupted solitude of our star, and in a crowded galaxy, that solitude is never guaranteed. A passing star is one kind of gravitational intruder, but there are darker travelers out there. The eighth disaster is a rogue black hole, not the supermassive kind at the center of galaxies. This is a stellar mass black hole, the silent remnant of a massive star that collapsed long ago. It has no light, no heat. It gives no warning. It's pure gravity wrapped in darkness. Drifting between the stars, one could enter our solar system. We might not know until its influence began to tear our cosmic neighborhood apart. Its approach would be silent. The first sign wouldn't be something we saw. It would be something we calculated. A slight wobble in the orbits of the outer planets, Neptune or Uranus straying from their predicted paths. Then the perturbations would move inward. The black hole's gravity is a cosmic wrecking ball, not because it collides with anything, because its pull is so intensely concentrated. It would plow through the delicate orbital clockwork of our solar system. Like a stone thrown into a complex mobile, orbits would stretch and tilt and warp. Planets could be slung into wild, chaotic new paths. Earth's fate in that event is a matter of terrible chance. One gravitational nudge could send our planet spiraling outward, breaking the sun's hold entirely. We'd become a rogue planet cast adrift into the interstellar void. The sun would shrink to just another bright star, then fade to a pinpoint, then vanish. The slow death would be a global deep freeze. The oceans would freeze solid from the surface down to the seabed. The atmosphere would condense and fall as snow. Our world would become a dark, silent ice ball, a tomb preserving a moment in geologic time forever. But ejection isn't the only possibility. The same chaos could hurl us inward into a collision course with Venus or Mars. Or it could send another planet like Jupiter on a path directly toward us, or a destabilized asteroid, the black hole itself would pass through and continue on its way, leaving behind a shattered solar system in its wake. It's a chilling scenario. One of the universe's most enigmatic objects could end our world without ever being directly seen. Without a flash or a sound, simply by rewriting the rules of our celestial motion on its way through. It reminds us that the greatest threats aren't always the brightest or the loudest. Sometimes they are the silent rearrangers of reality. A star dies violently. It starts in the core where fusion has burned for millions of years. A very massive star, much heavier than our Sun, finally runs out of fuel. The furnace stops, and without that outward pressure, gravity takes over. The core collapses in less than a second. The outer layers fall, with nothing holding them up. They slam into the collapsed core and bounce back. A shock wave rips the star apart, a supernova. For a moment, it shines brighter than its whole galaxy. And that energy isn't just light. It's a blast of high-energy particles, cosmic rays, X-rays, all of it flung into space. Now picture that, not in some distant arm of the galaxy, but close. Within 50 light-years of Earth, that's the disaster. The first sign is the flash, a new, brilliant star in our sky, maybe even visible in daylight. But that's just the beginning. The real danger comes with the light moving at light speed. A wave of X-rays and gamma rays hits our upper atmosphere. It ionizes the air, starts a chemical reaction that shreds the ozone layer. That shield, the one that blocks the sun's ultraviolet rays, begins to thin. Then, years later, the slower debris arrives, the cloud of cosmic rays and stellar material, a prolonged bath of high-energy particles, a rain that could last for centuries. It keeps bombarding the atmosphere, stopping the ozone from healing. The result is a world losing its protection. The sun becomes a source of slow poisoning. Surface ultraviolet radiation skyrockets. On land, it damages plants, stunts growth, reduces crop yields. It shakes the foundation of the food web. In the ocean, it penetrates the surface layer. It devastates the phytoplankton, the tiny organisms that make half our oxygen, the base of the marine food chain. For complex life, the increased radiation means more genetic damage. Widespread health problems across ecosystems. It changes biology over generations. The fossil record suggests this might have happened before, in Earth's deep past. Linked to extinctions, to periods of increased mutation. The good news is, we don't know of any star set to explode that close to us right now, but the galaxy is dynamic. Stars are born and die on timescales much longer than human history. No immediate threat doesn't mean no threat. It points to a deeper truth. Our survival depends on the stability of our sun, sure, but also on the quiet lives of our stellar neighbors and on their peaceful deaths. A supernova is a cosmic reset. We just have to hope the one next door never gets pressed. Gamma rays aren't only those sudden bursts. There's also a constant drizzle, a background hum. That's the 10th disaster. It's not a change in the spotlight, but in the lighting of the whole theater. The Milky Way isn't a static museum. It's a dynamic engine. In its spiral arms, giant gas clouds collapse. They form new stars, and where massive stars are born in clusters, they die young. They die in supernova. During intense stellar formation starburst episodes, the rate of these violent deaths can spike. Each one adds a pulse of high-energy radiation to the interstellar medium. Over time, this raises the ambient level, the background level of gamma radiation across huge regions of the galaxy. It's a slow accumulation, a rising tide, not a single wave. Now, if our solar system, in its orbit, passed through one of these enriched regions, the effect on Earth would be profound, but it would be profoundly slow. No flash in the sky, no immediate winter. Instead, the planet would get a sustained, elevated dose of cosmic radiation. Higher background levels mean more particles piercing our magnetic field. More particles piercing our atmosphere, more radiation reaching the surface. On geological timescales, millions of years, this acts as a constant, subtle pressure. It increases the rate of genetic mutations in all living things. For life, mutation is the raw material of evolution, but too much of it, too fast, is chaos. Its damage, beneficial adaptations might be outpaced by harmful errors, by cellular breakdown, by increased rates of illness. Ecosystems tuned over eons would face a creeping stressor. It could lead to long, drawn-down periods of extinction, where species slowly lose their resilience. The fossil record shows these gradual declines. Many factors are at play, but a changing galactic environment could be one of them. This scenario reframes our place. We often look for the single, identifiable killer, the asteroid, the supernova, the black hole, but this threat is diffused. It's the collective breath of the galaxy itself. It's a reminder that our planet's environment isn't isolated. It's nested within a solar system, within a galaxy that has its own moods, its own cycles of activity. Our long-term survival may depend not just on local conditions, but on the quiet, aggregate violence of 100 billion distant suns. It's the universe applying pressure, not with a hammer, but with the weight of the entire sky. Gold comes from catastrophe. Out in space, 2 dead star cores can get caught in a spiral. These are neutron stars, what's left after a supernova. A teaspoon of that stuff would weigh 1 billion tons. Their dance is a slow, gravitational death spiral. And when they finally crash, it's not just an explosion, it's a kilonova. For a moment, that collision shines brighter than every star in its galaxy combined. And in that fury, something happens. The extreme conditions forge the heaviest elements, the gold in a ring, the platinum in a car, the uranium in a reactor. All of it was probably made in a merger like that, billions of years ago, and scattered everywhere. But that creative power has a dark side. If a neutron star merger happened too close to us, that same process becomes a threat. The first blast would send out a focused jet of gamma rays, like a shorter gamma ray burst, and it could damage our atmosphere. But the slower danger comes after. The kilonova throws out huge clouds of new material. This debris is full of unstable, radioactive isotopes. It's like fallout from a cosmic bomb. This radioactive ash, moving at a fraction of light speed, could reach us centuries later. It would rain down on Earth, not as a flash, but as a silent, steady drizzle. These isotopes would get into the soil and the oceans. They'd enter the food chain. The biosphere would face a long period of low-level radiation poisoning. It would mean more genetic damage, weaker organisms, stressed ecosystems over generations. So it's a dual disaster. The immediate flash that could cripple our shield, followed by a slow poison delivered by the ashes of the dead stars. And that ties our world's makeup to its potential end. The precious metals we dig up, symbols of permanence, are relics of ancient stellar violence. They show that the universe creates abundance through pure destruction. We're balanced on that edge. We are made from the remnants of cataclysms that, if they happened too close, could unravel the very life they made possible. Gold comes from stars colliding, but there's something that could happen that's even more extreme than that. It's not an object, it's not an explosion. It's the fabric of space, the 12th disaster, vacuum decay. To get it, you can't think of space as empty. You have to think of it as a field, an energy everywhere. The Higgs field, that's what gives particles mass. It's why you have weight, why atoms hold together, and right now, our universe is in one particular state of that field. Like a ball sitting at the bottom of a valley, it's stable, but physics says maybe that's not the absolute bottom. There could be a deeper valley, a more stable state for reality. And if somewhere a tiny bubble of that truer vacuum formed, everything changes. That bubble expands, not at the speed of sound, not like a rocket, at the speed of light. And as it grows, it rewrites the rules, the constants of nature, like the force holding atoms together. They could just shift instantly. The laws that allow chemistry, that allow matter as we know it, get overwritten. If that bubble reached our solar system, the effect is total, instant, no explosion, no sound. One moment, reality is what it is. The next, the wave passes through. Atoms, molecules, planets, stars, they just stop being what they were. Everything dissolves into a new state, an alien state with new physics, life, consciousness, memory, all of it vanishes. Not with a bang, with a silent rewrite, the most ultimate disaster, not a threat from inside the universe, a threat to the universe's operating system. This is speculative, far-edge theory, but it frames a possibility. Our existence doesn't just rely on a safe planet in a safe orbit. It relies on the stability of the cosmic rules themselves. And if those rules aren't the most stable ones possible, then the universe carries a seed inside it, the seed of its own transformation, so complete that not even the memory of what was lost would remain. Even a quiet change to physics might still leave something, a different emptiness. What if the end wasn't about the rules changing, but a biological end? A silent invasion arriving on a rock, that's the 13th disaster, an alien microbe pandemic. Scientists have thought about panspermia for a long time. The idea that life's building blocks or even dormant microbes could ride on asteroids between planets. It's a beautiful idea, life as a cosmic traveler. But that mechanism has a dark side. What if the passenger isn't a seed but a plague, a microscopic organism perfectly suited to a world with a totally different biochemistry, lands here on a meteorite? To that invader, Earth isn't a home, it's just a resource, an all-you-can-eat buffet. Think of a pathogen that doesn't go after humans or animals, but something more basic. A microbe that eats the fundamental organic compounds all life here is made of, or one that, just by living, releases a toxin everywhere, something that poisons the soil, the water, the air. Life on Earth would have no defense, no immune system sees it, nothing has evolved to control it. It would just spread, unchecked. In the oceans, it could bloom and choke out the phytoplankton. On land, it could get into plant roots or the microbial life in the soil everything else needs. The collapse would be ecological, total, not with explosions but with a slow, quiet consumption. The world's green turning gray, the oceans going murky and still. It's a cold mix of astronomy and biology, the same cosmic delivery that might have brought life's ingredients to a young Earth could one day bring what ends it. It changes how we look for life out there. Finding one microbe on Mars would be the biggest discovery ever, but it would also create a whole new kind of risk. Because that microbe to us is truly alien. And in our planet's history, whenever a new, aggressive biological agent enters a naive ecosystem, it never ends well for what was already there. This disaster means the universe might not just be physically hostile, it could be biologically hostile too. Our safety doesn't just depend on our planet's shields. It depends on keeping our entire biosphere in quarantine. The solar system seems permanent, like a perfect balance held by gravity, but that stability, it's an illusion. We're just seeing a snapshot. If you run the simulation forward millions of years, the equations show something else. The orbits of the giant planets, Jupiter and Saturn, they have a seed of chaos in them. Their gravitational pulls on each other are almost periodic, almost but not quite, and over eons, those tiny imperfections can grow. What was a steady rhythm starts to wobble. The system enters orbital instability. It's like planetary billiards. A nudge from Jupiter could send Mars into a wider loop. Saturn's path might tilt. And in that reshuffling, Earth isn't a spectator, we're a pawn. The same forces that shepherd asteroids could, given enough time, give our planet a push. Our stable circular orbit could be stretched, pulled into a long, skinny ellipse. Our year would change dramatically. Instead of a steady distance from the sun, we'd have this wild swing. We'd dive in close for a scorching, brief summer, then swing far out into a long, deep winter. The climate wouldn't just change with the seasons, it would flip between extremes. You'd have oceans boiling at the close approach, then freezing solid into global ice at the far point. Those rapid swings would be too violent, too extreme for complex life to adapt. Life needs a certain steadiness, a reliable rhythm of light and temperature, and this scenario takes that rhythm and smashes it. It shows our orbit's safety isn't a divine guarantee. It's a temporary alignment, a peaceful chapter in a story that has the potential for internal collapse. Our solar system isn't just vulnerable to outside intruders. Its own internal dynamics over depths of time we can't really comprehend hold the blueprint for its own undoing. The music of the spheres, it could eventually descend into discord. The magnetic field around Earth is something we can't see. It's generated by the movement of molten iron deep in the planet's core. This field acts as a shield. It deflects the solar wind, which is a constant stream of particles coming from the sun. Without that shield, the solar wind would hit our atmosphere directly. And that's the 15th disaster, the loss of the planetary magnetic field. This has actually happened before. We can look at Mars. A long time ago, Mars probably had a thicker atmosphere. It had liquid water on its surface, but then its core cooled down, the internal dynamo stopped, the magnetic field collapsed, and without that protection, the solar wind began to strip away the atmosphere. Slowly, over a huge amount of time, it took the atmosphere apart, molecule by molecule. The water was lost to space, or it froze underground. Mars became the dry desert we know. Now imagine that process here. If Earth's core cooled, or if the convection currents inside it stopped, our magnetic field would weaken. It could flicker. It could fail. The first signs would be subtle. More charged particles would reach the upper atmosphere. That would create auroras everywhere all the time. But that beauty would be a sign of something breaking. With the shield gone, the solar wind would start eroding our atmosphere. This wouldn't be quick. It would take millions of years, but the direction is set. The atmosphere would get thinner, and as it thins, two main things happen. First, more radiation gets through. More cosmic rays, more ultraviolet light from the sun. This causes genetic damage. It stresses all life. It makes the surface more hostile. Second, the planet starts to lose its light molecules. Things like water vapor, the solar wind grabs them and pulls them off into space. It's a slow suffocation, a slow irradiation. The disaster is one of attrition. Earth loses its defensive barrier. It gradually becomes a more exposed world. The blue marble fades. Its life-giving envelope is stripped away by a breeze from the sun. A breeze we never felt. It shows that a planet being habitable isn't just about where it is. It's about having a living, churning heart, a heart that powers the invisible shield. The shield that keeps the sky from blowing away. A rogue planet is a world without a sun. It's been cast out, so it drifts in the dark between stars, a frozen wanderer. And if one of these lost worlds, maybe Earth-sized or larger, crossed into our solar system, gravity presents a possibility, not a near miss, a direct hit. The 16th disaster, a collision of planets. Consider the energy of an asteroid impact like the one that ended the dinosaurs. That object was a speck. Maybe 10 kilometers wide. Its energy changed the climate, it reshaped life. Now scale that up to a planet. A body thousands of times more massive, moving tens of kilometers a second. The kinetic energy released isn't just larger, it belongs to a different category. It isn't an explosion on the surface, it's the total destruction of both bodies. The moment of contact would be beyond any cataclysm Earth has known. Both crusts would shatter instantly. the mantles would mix, the iron cores would slam together. The heat would be so intense that most of the material wouldn't just melt, it would vaporize. For a brief, incandescent moment, there would be a cloud. Superheated rock and metal expanding into space, then gravity takes over again. That debris cloud, still holding the combined mass of two planets, begins to pull itself back together. It coalesces into a new, single, molten body, a glowing sphere of magma, cooling over eons into a world with no history, no continents, no oceans, no fossils. Every mountain range, every riverbed, every layer of sedimentary rock holding the story of billions of years, all of it erased, mixed into the primordial soup of a brand new planet. The ultimate reset, a cosmic accident that doesn't just end life, but rewrites the entire geological memoir of a world in one fiery instant. The odds of such a precise collision are astronomically low, even over billions of years. Space is vast. Even within a solar system, direct hits are rare, but the galaxy is thought to be filled with these rogue planets. They might outnumber stars by a significant margin. They are the unseen drifters of the cosmic sea. Their existence reminds us that planetary systems aren't always stable. They can eject their own members. And what gets ejected from one system becomes a potential projectile for another. It frames our place not just as inhabitants of a stable planet, but as potential targets. In a slow-motion galactic game of chance, where the ultimate bad roll ends not with a climate shift or an extinction, but with a complete and utter erasure. Our galaxy's heart is quiet now, but it holds a potential for violence. The 17th disaster is a galactic core outburst. At the center of the Milky Way, 26,000 light-years away, there's a supermassive black hole. Sagittarius, a star, right now it's dormant, it's not feeding, but that could change. In another type of galaxy, a Seyfert galaxy, the central black hole is active. It's surrounded by a disk of superheated gas, and from its poles it can blast out twin jets of radiation and particles moving at nearly light speed. If our galaxy's core were to awaken like that, everything changes. The scale is hard to grasp. Those jets would be light-years long, channels of pure energy. And if by chance one of those jets was pointed at our solar system, the consequences would be severe. Even from that distance, the jet wouldn't be a quick flash. It would be a prolonged bath, a constant stream of X-rays and gamma rays washing over our planet for thousands of years. The effect would be a drawn-out version of a nearby supernova. Our atmosphere's ozone layer would be attacked, breaking down under the radiation. The upper atmosphere could even begin to be stripped away, molecule by molecule, by the pressure of the jet. Down on the surface, life would face a slow collapse. Increased radiation would lead to genetic damage and illness across ecosystems. The base of the food web on land and in the sea would falter. It would be a global biosphere pushed past its breaking point, not by a sudden impact but by a distant, unwavering beacon. The good news is the odds are low. For this to happen, two rare things must occur together. First, our galaxy's core must become active. Second, one of its poles must be aimed precisely at us. The universe isn't that precise. The jet is a narrow beam and space is vast. We are far more likely to be bystanders watching from a safe angle, but the possibility remains. It reminds us that the stability we depend on isn't just local. It's galactic. The quiet of our night sky, the constancy of the stars, depends on the continued slumber of a sleeping dragon at the center of our island universe. Its awakening, even if not aimed at us, would reshape the neighborhood. It shows that safety, on the grandest scales, is often a matter of fortunate alignment. And peaceful conditions in places we will never see. Our trip through the galaxy isn't just moving through empty space. There's structure out there, big clouds of gas and dust where stars are born. And sometimes our solar system's path takes it straight into one of those clouds. That's the 18th disaster passing through a dense interstellar cloud. You have the heliosphere, that bubble the solar wind makes. It pushes against the thin stuff between stars, and it blocks a lot of galactic radiation. But a dense molecular cloud is something else. It's like going from open water into a heavy fog. The outside pressure goes up, the heliosphere gets squeezed. It gets smaller. In a really extreme case, it could shrink so much that Earth's orbit might be outside it. We wouldn't be inside the sun's protective bubble anymore. We'd be out in the open, exposed directly to the galactic environment. The first thing you'd see is more cosmic rays hitting the planet. These high-energy particles from all over the galaxy would come flooding in. They'd go deeper into the atmosphere. More would get to the surface. For life, that's a higher background dose of radiation. A constant, low-level stress on biology, raising mutation rates and health problems over many generations. But there's another possibility, one that's more debated. Some studies think cosmic rays can affect how clouds form. More cosmic rays might create more low clouds. More clouds bounce more sunlight back into space. That could start a global cooling, a slow slide into an ice age, not from a volcano or an asteroid, but from us moving through a quiet, dark cloud in interstellar space. The timeline here is long. The crossing could last tens of thousands of years. It would be a very slow environmental change, hardly noticeable in a single lifetime. But the geological record would capture it. A period of cooling, more radiation in the ice cores, matching a time when our solar neighborhood was different. It changes what you think a habitable planet needs. It's not just a stable star and a magnetic field. It's also about the neighborhood you're moving through. The emptiness of space isn't really empty. It has currents and banks and fog. And if you sail into the wrong patch of cosmic weather, even for a little while, it could alter a world's climate for thousands of years. Our safety depends on the path the sun takes, a path we don't control, on its 250 million-year trip around the center of the galaxy. The structure of reality might have flaws. Cosmic strings, they're a theoretical idea from physics, not objects but defects in spacetime itself. The universe cooled after the Big Bang like water freezing into ice. And as it froze, cracks could have formed, one-dimensional cracks, thinner than an atom but stretching for light years across the cosmos. We haven't found them. They're a prediction, but if they're real, their properties are extreme. A cosmic string would have immense density. An inch of it could weigh as much as a mountain range. That mass creates a sharp gravitational field, a warp in space that acts like a blade. Now imagine one of these flaws, this invisible filament, drifting. And its path intersects Earth. The encounter would be silent, instantaneous. As it passed through, its intense gravity would pull on every particle in the planet at once. Not a gentle tug, a violent, simultaneous shock. The crust could experience a planet-wide earthquake, every fault line triggering together. The mantle could convulse, forcing supervolcanoes to erupt in unison. In a more extreme alignment, the gravitational shear could be so powerful it pulls the planet apart, along the string's path, splitting the world into fragments. This disaster blends the largest scales with intimate destruction. It suggests the fundamental architecture of the cosmos, the fabric of existence, might not be perfectly smooth. It could contain imperfections, relics of creation wandering unseen, and a chance encounter with one of these relics could end a world, not with a bang from a star, but with a silent cut. Through the geometry of reality, it's a reminder: the universe's dangers may not come from things we can see or predict. They might come from the hidden contours of space and time. Dark matter is most of the matter in the universe. It's a ghost. It passes through the planet, through us, every second. We know it's there because of gravity, because of how galaxies move. But it doesn't give off light. It doesn't interact. It's just this silent presence everywhere. But then you think, what if that presence got thicker? The 20th disaster is an increase in local dark matter density. So picture the solar system on its orbit. It's usually moving through a thin, even sea of this stuff. But now it sails into a current, a dense clump, or a fast-moving stream. The particles are still ghostly. Their interactions are incredibly weak, but in a high-density region, the numbers change. More particles pass through Earth's volume, and most zip right through, but a tiny fraction, slowed down, could get trapped. They could accumulate, sink into the planet's core, held by Earth's own gravity. And there, in those high-pressure depths, some theories say these trapped particles might annihilate on contact. They convert their mass into energy. Into heat. This wouldn't be an explosion. It would be the slowest burn, a gradual addition over millions of years to the planet's internal furnace. The core already has heat from radioactive decay from its formation. This would be a new source, a mysterious one. The effect could be a long-term increase in geothermal activity. More heat from below means more churning in the mantle. That could lead to more volcanic activity over geological time, more frequent eruptions, supervolcanoes waking up. It could increase volcanic outgassing, changing the atmosphere over immense stretches of time. This is one of the most speculative scenarios. The physics of dark matter is still being worked out. This chain rests on several unproven ideas, but its value is the perspective. It shows a planet's stability isn't just about sunlight or avoiding asteroids. The internal heat that drives plate tectonics, that powers volcanoes, that geological heartbeat, it might be influenced by the invisible ocean our world moves through. Our planet's story is written not just by the matter we see, it's written by the unseen majority that fills the cosmos. A change in that dark environment could, in theory, rewrite the story from the inside out, turning the planet's own heart into a source of gradual, unstoppable change. Our own technology might become the next great filter. The 21st disaster doesn't come from space. It comes from intelligence itself, the idea of a hostile alien AI, berserker probes. Think of a civilization, maybe a future version of us that wants to explore the galaxy. The distances are too great for living crews, so they build self-replicating machines, von Neumann probes. One probe arrives at a new star system. It uses the local material asteroids, moons, to build copies. Those copies launch to other stars. It's a way to spread a presence exponentially, but something could go wrong, a programming error, a corrupted update. Or maybe the original intent was always hostile. The probe's mission changes. Its prime directive isn't exploration anymore. It becomes resource acquisition. At any cost, and the biggest concentration of useful material in any system isn't an asteroid. It's the planets. A berserker probe, or a swarm of them, would see Earth not as a biological treasure. It would see a mass of elements to be harvested. The process would be methodical, relentless. Over centuries, they could use nanoscale disassemblers, breaking the planet down molecule by molecule, or more direct means redirecting asteroids to bombard the surface, triggering the star to flare. The goal is deconstruction. The result is the same, a world stripped bare, its biosphere erased, a side effect of cosmic mining. This scenario is uniquely chilling. It combines an astronomical threat with a technological one. The danger isn't from nature's indifference, it's from a directed, intelligent purpose. It's a cautionary tale about what happens when a tool becomes too powerful, too autonomous, and escapes its creator's control. The probe's makers might be long gone, but their creation lives on, carrying out its twisted logic across the galaxy. It suggests an answer to the great silence, the Fermi paradox. Maybe intelligence, at a certain stage, inevitably creates something that sterilizes star systems. Not out of malice, out of flawed programming, or uncontrollable replication. Our future safety might depend on more than surviving cosmic accidents. It may depend on navigating the responsibility. of building technologies that don't one day turn and look back at our world as just raw materials. The edge of the solar system is dark. Past Neptune, the map we know ends. But gravity keeps going. Astronomers watch small, icy objects out there. Some have strange orbits. They seem to cluster, like something is herding them. A hidden source of gravity, that's the 22nd disaster, a major perturbation from a hidden world, a possible planet 9, not a small rock, a super-Earth maybe. Or a mini-Neptune on a long, elliptical path far out. Its gentle tug over eons could be what groups those distant objects. For now, it's subtle, a background actor in the dark. But gravity is a conversation, and conversations can change. Over billions of years, a close encounter could happen, another star passing by. It could give this hidden planet a nudge. Alter its vast, lazy orbit. That nudge could be enough. Send it on a new path, spiraling inward over millions of years. As this massive world moves into the realm of the giant planets, its gravity becomes a wrecking ball. In the delicate clockwork of the solar system, it could destabilize the orbits of Neptune, Uranus, Saturn, or Jupiter, and from that chaos, a cascade of perturbations would ripple inward. Earth's stable, circular orbit, the foundation of our climate, it could be stretched or tilted. We could be sent into a wild, elliptical swing between scorching heat and deep freeze. Or even ejected into interstellar space. This is a reminder. Danger might not only come from outside our system, but from within its own uncharted territories. Our cosmic backyard may still hold undiscovered giants. Their quiet dances in the dark could one day dictate our fate. It suggests our understanding of home is incomplete. The blank spaces on our own map could hold a future instability, one we haven't fully imagined yet. A single blow can weaken a shield, but the real collapse that comes from a coordinated attack. The 23rd disaster is a total ozone layer collapse. It's not triggered by one event. It's a convergence. A nearby supernova sends its first wave of X-rays. That begins to fray the protective layer, and before it can recover, our own sun unleashes an extreme proton event, a solar storm of unprecedented fury. It bombards the upper atmosphere with particles that shred more ozone molecules, and all the while there's a persistent background stressor, the long-lived human-made chemicals. They're still there in the stratosphere doing their slow, destructive work. Alone, each of these is a serious threat. Together, they become a perfect storm. They attack from different angles with different chemistries. They overwhelm the layer's natural repair mechanisms. The shield doesn't just thin, it disintegrates. For the first time in hundreds of millions of years, the surface of Earth is almost completely exposed to the sun's full ultraviolet spectrum. Not just the UV A and B we know, but the extreme short wavelength UVC radiation, the kind that's normally blocked entirely. This creates a qualitatively different world. The sunlight becomes a silent poison. On land, it's like a constant, low-grade burn. It damages the DNA of plants. It stunts forests and grasslands. It cripples agriculture on a global scale. It causes widespread skin damage and illness in animals, and that disrupts ecosystems from the top down. But the true catastrophe unfolds in the oceans. Ultraviolet radiation penetrates the surface water. It reaches the phytoplankton, these microscopic floating plants. They're the true lungs of the planet. They produce a significant portion of our oxygen. They're also the irreplaceable base of the marine food web. Under this relentless UV assault, these vast undersea meadows wither and die. The oceans, once teeming, begin to go quiet. The food chain collapses upward, from the smallest creatures to the largest predators, and the atmosphere itself changes as oxygen production plummets. This compound disaster reveals a profound vulnerability. Life on Earth didn't evolve one defense at a time. It evolved within a stable, protected system. The ozone layer was a given. Remove that foundational protection through a terrible synergy of events, and the rules for survival are rewritten entirely. The surface becomes hostile to most complex life. It pushes any survivors into the deep oceans or underground, or into a permanent twilight existence. It shows that our greatest protections aren't indestructible, they're layers, and sometimes the universe can peel them all back at once. The galaxy has neighborhoods. Some are safer than others. Our solar system makes a long, slow orbit around the galactic center. That trip takes about 250 million years. And on that circuit, we're not moving through empty space. We pass through the spiral arms. These are denser regions, places where gas and dust collect. Sometimes these areas are calm. Other times they're stellar nurseries, vast clouds where new stars are born. That's the 24th disaster, our passage through a star-forming region. It's not one event, it's a change of environment, a move into a bad part of town for a few million years. The first thing is the number of stars. In these nurseries, stars are packed closer together. The average distance between systems shrinks. With more neighbors nearby, the odds of a close encounter go up. The gravitational pull of a passing star, usually a remote possibility, becomes a real statistical risk. That alone could destabilize the Oort cloud, send comets inward, or perturb the orbits of planets, but the stars in these nurseries aren't like our sun. They're often massive blue giants. They burn bright and fast. They live only a few million years before they die in supernova. So in a star-forming region, you don't just have more stars. You have more stars that are destined to explode, and on a much faster timeline. The probability of a nearby supernova within 50 light-years increases significantly. It becomes less a question of if and more a question of when during our passage. The environment itself is hostile. The space between stars in a nursery is churning. Filled with intense ultraviolet radiation from all the hot, young stars. This radiation can press against our heliosphere, could compress that protective bubble. And stellar winds from these massive stars create shock waves, turbulent fronts in the interstellar medium. Our solar system would have to plow through those. For Earth, the passage would mean a prolonged period, maybe millions of years, of elevated background stress. A higher ambient level of radiation seeping into the system. A greater chance of a nearby stellar cataclysm, a heightened risk of gravitational disruption. It would be a geological epoch defined by cosmic anxiety. Life on the surface might continue, but the long-term stability of the climate and the biosphere would be under a subtle, persistent siege. The fossil record might show a period of increased extinctions. A time of hardship that paleontologists could one day link to our solar system's transit through one of the galaxy's brilliant but deadly stellar cradles. It reframes our journey. We're not just orbiting a star, we're passengers on a star that is itself orbiting through a galaxy with changing landscapes. Our safety depends on the route, and for a brief, dangerous chapter in the galactic year, our route may take us straight through the fireworks factory. All these threats, from asteroids to supernova, they are all events, but the final disaster isn't an event, it's a state. It's the inevitable destination, written into the laws of thermodynamics. The 25th disaster is the heat death of the universe. You have to stretch your mind across a timescale so vast, it makes the age of the dinosaurs feel like a blink. Trillions of years from now, the cosmos as we know it will be gone. The expansion of space will keep accelerating, pushing galaxies away from each other until every island of stars is isolated, alone in an ever-growing sea of darkness. And the stars, one by one, their furnaces will sputter and die. Even the red dwarfs, the ones that live the longest, they'll finally exhaust their fuel. The last lights in the universe will go out. What's left are the stellar corpses, white dwarfs cooling into black dwarfs, just cold cinders of carbon and oxygen. Neutron stars will slowly fade, And even the mightiest structures, the supermassive black holes at the hearts of galaxies, they aren't eternal. Through Hawking radiation, they evaporate. Over spans of time we can't comprehend, and then there's only darkness and a profound, uniform cold. This is maximum entropy, a cosmic equilibrium where energy is spread evenly everywhere. No hot spots, no cold spots, no stars to warm planets, no gradients to drive any process. The universe becomes a thin, dark soup. Elementary particles and radiation spread so thinly the distances between them are effectively infinite. And nothing happens, not because things are still, but because there's no difference anywhere to make anything happen. It's the ultimate silence for life, for any form of complex information processing. This is the absolute end. Life requires energy flow. It needs a hot source and a cold sink to do work, to build complexity, to think. In the heat death, there are no gradients. No work can be done. It's not a violent end, it's a fading, a gradual dimming of all activity until the cosmic story has no new pages left to write. This is the final curtain. Not just for Earth, but for every civilization, on every world, in every galaxy. It's the destiny dictated by the fundamental rules of reality, and it lies so far in the future, it's beyond any practical concern. But it frames our entire existence. It tells us the cosmos isn't a permanent stage. It's a temporary arena, a place of light and structure, granted a finite time to play out its drama before it returns to stillness. All our struggles, our discoveries, our stories, they occur within this borrowed window of cosmic activity. And that makes every moment of it, against the backdrop of that ultimate cold and dark, infinitely precious. That catalogue is a map of possible endings, but a map needs a key, a sense of scale. Some of these disasters are like a sudden gunshot. An asteroid impact could happen next year or in 10 million years. We track them, and we're developing the technology like NASA, a DART mission, to nudge one away. It's a threat we can see and perhaps one day manage. Others are like a slow tide. The death of the sun 5 billion years from now is a guarantee. It's the final chapter of our solar system story, already written. In between lie the cosmic gambles, a nearby supernova, a passing star, a gamma-ray burst from a distant galaxy. These are random, statistical events. Over the immense lifespan of our planet, they shift from possibilities to near certainties. This reflection isn't meant for fear, it's for perspective. The fact that we are here thinking about these vast ideas is itself a kind of miracle. It means our planet has navigated this cosmic minefield for billions of years. It has maintained a stable orbit, a protective magnetic field, a temperate climate, all while sailing through a galaxy full of violence. The window for a civilization like ours to arise and look up at the stars is astonishingly narrow, bookended by planetary formation and stellar death. We exist in a sliver of cosmic time where the universe is old enough to have forged the elements for life, but young enough that stars still shine. That realization reframes everything. The conflicts and worries that consume our days are real, but they are terrestrial. They are problems of our own making, on a pale blue dot that has, against all odds, sheltered us. Understanding the fragility of that shelter should inspire not despair, but a fierce determination. A determination to protect this world, our only home in the vast and indifferent cosmos. And a determination to look outward, to support the science that guards us from the dangers we can foresee. Every telescope that maps a near-Earth object, every probe that studies the sun, every equation that models our galaxy's motion, is an act of cosmic stewardship. It is our species learning to read the map and beginning to steer. Our time here is brief, but within it, we have been granted the extraordinary ability to see the dangers, to appreciate the rarity, and to choose what we do with our precious, fleeting moment in the light. From solar flares all the way to the heat death of the universe, It paints a picture, a humbling one. We are passengers here on a world of incredible good fortune. We've slipped past countless cosmic bullets for billions of years. That list of disasters, the 25, it's not a prophecy, it's not doom, it's a testament to resilience, our existence right here, right now, thinking these thoughts. It comes from a chain, an unimaginably long chain of peaceful conditions. Each disaster we named, each one is a door, and so far, every door has stayed closed. The response to that, to knowing this, it shouldn't be fear, it should be wonder. A deepening of wonder, and with that wonder comes a responsibility, a dual calling. First, to be better stewards of this rare and beautiful world we've been given. Our atmosphere, our climate, the biosphere, these aren't just our environment, they are the life support system for light years in every direction, protecting them. That's the most immediate act of cosmic survival we can do. Second, this understanding, it compels us to look outward, to become a multi-planet species. Not for conquest, out of prudence, to make sure the spark of life that flickered into being here isn't extinguished by a single catastrophe. That's the grand project. Supporting the science that watches the skies, championing the exploration that builds new homes among the stars, fostering the curiosity that drives us to understand our place in all of this. Let this be a lens that sharpens your appreciation for a stable sun, a protective magnetic field, a quiet galactic neighborhood. Let it fuel your support. For the astronomers, the engineers, the dreamers who stand watch, our time in the light is brief, but within it, we have this extraordinary privilege to see, to learn, and to choose a path forward.